Hey, I wanted to share with you today a little sneak preview into a paper we will be sending today for peer review. But I'm pretty excited about it because it's the kind of the culmination of a 3 year long project, my Fondesit Iniciación project, which is the first research grant I had. Now I have a new research grant that will take this research into new directions. But this is some exciting results. So what do we have here? We have Santiago, Chile over here, and we over here draped over that is San Ramon Fault. So San Ramon Fault is a shallow fault which is at the foot of the Andes, which can generate pretty significant earthquakes as far as our estimation goes. Whether it's active or not, and it will shake again, is controversial. But my research aims at answering the question, what will happen? And this is the specifics. So we start by modeling the fault. So these are different kinematic source rupture models that tell us the details of how this fault behaves. The fault is 30 kilometers in length, 16 kilometers in width, and dips kind of in a 16-degree angle. So you can imagine it dipping into the mountains, underneath the mountains. And we have different sites, and at these different sites, what we do is we propagate the rupture from the source to the different sites, and we see what happens. And specifically in this paper, what we're looking at is different modeling strategies and how different engineering demand parameters like, I don't know, floor acceleration or interstory drift might be influenced by your modeling strategy in this particular case. So first I want to show you here a little video of what the rupture propagation looks like. We have here something that is kind of like the area of Santiago, and we have selected um, a point here, and we'll see this acceleration time series from the simulations coming up. Now, this nice little app that's showing the video is created by Patricio Palacios, one of my PhD students, who's a wizard with doing all these things. So we'll see what the propagation kind of looks like from the source to the site, and you can see kind of like the directivity pulses, how they look like, and the complexity. Now, the crustal model is one-dimensional and layered. So all this complexity that we're seeing is not coming from the crust, it's coming from the source. So that's our main contribution to this complexity that you see here. Now, if we go to a particular building, I'll show you another video real quick. Here we go. Let me move stuff around. Now, there's a finite element model of a 10-story building. This is by my other PhD student, Nicolás Bowen, both awesome people, great engineers and great modelers who are leading this study. So here we have a soil box. We'll soon see DRM motions, so fully three-dimensional motions coming into this model. And we have a non-linear building here. Everything is non-linear in this building. So the walls, the columns, the slabs, just everything breaks if you excite it strongly enough. And here we won't see the damage in the color scale. We'll see displacement. So we'll kind of get a feeling of how DRM puts motions into these models. Here we go. So you'll see first there's and the displacement here is amplified. So you can see a little bit of curvature there. It's coming from the self-weight or the deformed shape after the self-weight application. We didn't subtract that out from the building. It's all there. Here we go. Come in some motions. And right off the bat, you can see, I'm going to pause it right there. You can see the ground just shifting, but it shifts in this weird pattern. And this is an artifact of using the domain reduction method, DRM, to input ground motions into a model such as this. So you set up a layer, and that layer is where some equivalent forces come in and they push the soil box around. And in this way, with this particular method, you can get the full complexity of the dynamic wave coming in. So you can get body waves, you can get surface waves, you can get inclined motion, you can get everything into the model. It's very sophisticated, but it requires this type of simulation where you simulate everything. And it creates this weird, this is not the soil moving like this for any other reason than the method. So to make it less painful to the eye, what we should do is just cut that box out and just show the building shaking. But here we go. The motion. These simulations, they take about 8 hours to compute. or something like that, or a couple of days maybe in my cluster using 16 processors. It's not a big deal. It's the seismic simulation, the one that's more expensive. So generating the motions. So this is what we're looking at. So this is the fanciest model of all the models we've explored. From here, we start making assumptions over this. So we're gonna start, looking at fixed base condition, or when you have springs at the bottom, or if you take away nonlinearity, or the way you even model the building. If you're doing rigid diaphragms or simpler models, we'll see how those results creep into your estimation of your engineering demand parameters, which is basically what we want to see. We want to see how the engineering demand parameters are affected by your choice of modeling. And what we're seeing is kind of worrisome. But you'll have to wait for the full paper to come out, which we'll send today, and maybe in a couple of months, if all goes well with the peer review, we'll get that paper out. And in that occasion, I'll do another video showing the full thing. Okay, see you guys next time.